All right, good morning. Am I audible?
Good morning, sir. Yes, you're audible.
Guys, hope all of you are safe because the situation is really grim now. Having a couple of incidents nearby my home, it's really disturbing this time. Okay, all right. So yesterday we discussed. Also not feeling that well. Yeah. Yesterday we discussed about. Just give me a second. I'll start recording and present the screen. Yeah. So yesterday we had a discussion on the Gauss-Markov theorem. We did a very basic proof where we proved that any linear combination of the population coefficient, that is a beta coefficient, and out of the class of all such linear and unbiased estimator, it is the OLS, that is the estimator obtained through the method of least square, gives you the smallest sample variance. That is what Gauss-Markov theorem is. And this is what, in short, it is referred to as that if all the assumptions of CLRM are satisfied, OLS estimators have the property which is referred to as blue property, that is best linear unbiased estimator. But you have to understand that Gauss-Markov estimators have the least sample variance. That's why it is referred to as best. And then we went ahead and discussed the statistical inference process, which where we utilize the concept of OLS estimators, because that's what our main aim as far as econometricians are concerned. That is, we want to test our hypothesis concerning the various aspects of about these population parameters. And that's where we discuss the test of significance hypothesis, where we want to test whether any of the population coefficient is statistically significant or not. And their statistically significance means that whether that particular coefficient should be included in the, or that variable should be included in the population regression function or not. Then we discussed various other some very simple examples of linear hypothesis, and in the last we discussed about the test of overall significance of relation. And that's where we discussed that all these linear hypotheses about the population parameter can be exactly thought to be fitted in a linear framework, which is written as R beta is equal to R, where R is a matrix of known constant having a dimension q by k, and here R is a vector of known constants having a dimension q. This beta is your population coefficient. So what it referred to was that जितने भी हम examples of linear hypothesis पढ़ते हैं, all of those examples can be exactly fitted into this general linear framework. Now moving ahead, our aim is to exactly understand how we utilize the concept of OLS estimators as far as testing the linear hypothesis about the population parameter is concerned. Yeah. So as we proceeded in the method of OLS as well, since we do not know about this, the best way or the best thing that we can do is we can replace this beta by the OLS estimators. So we can write this as RB is equal to R, or it can be stated in the null hypothesis form, RB minus R equals 0. Now, what this RB and R is, this is the actual observation. This is the estimated observation, because here we have utilized OLS estimators. So RB minus R is the difference between actual and expected. कि आपने जो expect किया, that is आपने जो hypothesize किया, and जो actual observation है आपके पास, अगर इसके बीच में difference बहुत ज़्यादा है, it means the null hypothesis, that is you tend to contradict your null hypothesis. And if the difference between expected and actual values are not that large, we tend not to reject the null hypothesis. This is what, the basic applications or basic concepts around rejection or non-rejection of the null hypothesis is concerned. So basically what we say here is that the difference between actual and expected observation, that is RB minus R. RB is your estimated observation. R that we obtain is the actual observation. So तो जो हमारा टेस्ट प्रोसीजर है मोस्टली वो इसी डिफरेंस को टेस्ट करता है, whether this difference is too large or this difference is small. So अगर large होगा, it means जो भी आपने null hypothesis लिया है उस पे थोड़ा you tend to contradict your null hypothesis if the difference between actual and the estimated observation is too large. And on the other hand, if the difference is not too large, that it's small, then you tend to not reject the null hypothesis. Now I'm sure that you understand this, that we never say that we accept the null hypothesis. We always say we do not reject the null hypothesis. It is not you accept and do not accept. No, you reject the null hypothesis. When do you reject the null hypothesis? You reject the null hypothesis when the difference between the actual and estimated observation is quite large. And you do not reject the null hypothesis when that difference is small. Now, how do we actually determine whether this difference between the actual and estimated observation is large and small? It will be determined by the sampling distribution that we have for the OLS estimator. और एक बहुत ही fundamental चीज है जिसको आप हमेशा याद रखिएगा, that you always test the hypothesis assuming null to be true. That is, you start with an assumption that your null hypothesis is true, and then you test your hypothesis. So if the difference is large, then you say that you contradict your null hypothesis. That is, जो भी आपने assume किया था true वो गलत है, and that's why you reject the null hypothesis. And if the difference is not that large, then what you assume, that is the null hypothesis being true, you do not reject that assumption. This is how the testing procedure goes. So the difference between the actual and estimated observation being large depends on or is determined by the sampling distribution under the assumption of null hypothesis being true. अब यहाँ पे मेरा null hypothesis क्या है? यहाँ पे मेरा null hypothesis है this R beta is equal to R. So any test that we undertake in order to check whether the hypothesis that we have is true or not, we all the time we assume that the null hypothesis is true. Now let us go ahead and try and understand how do we actually go about testing our hypothesis. Okay, all right. So अभी हमने क्या देखा that in order to carry on the test, the best thing that we can do is we can replace this beta by b. That is, we can replace this r beta is equal to r by r b minus r. This is a statistic because ultimately you're trying to guess about this beta. So we must have the sampling distribution of rb as well, because ultimately मेरा जो test statistic है इसी पे based है. So अभी हमने देखा था last to last lecture that mean of b OLS estimator is your beta. So expected value of rb क्या होगा? It will be r beta. So this is quite straightforward. So since we are trying to talk about the sampling distribution of this rb, so sampling distribution में मुझे mean पता चल गया है. That is expected value of rb is equal to r times beta. Now I need to talk about the variance of rb. So variance को हम simply ये देख सकते हैं कि जो मेरा b vector है या जो b OLS estimator का जो coefficient vector है, that is multiplied by a matrix of known constant written as capital R. So इसका अगर मैं वेरिएंस की बात करूं तो जो नॉर्मल वेरिएंस है b का उसमें सिंपली मुझे r को मल्टीप्लाई कर देना है. So नॉर्मल वेरिएंस ऑफ जो हम निकाले थे that was something like this. This got multiplied by its transpose. Now this is multiplied by r. So this multiplied by or post multiplied by its transpose can be written as b minus beta transpose r transpose. And this is how you calculate variance of rb. Now you can easily think that here I have, this is a matrix of known constant r and r transpose, so expectation can easily be calculated or taken over here. So I can write this as r expected value of b minus beta into transpose. Now this term is nothing but your variance of b. So variance of rb can be written as r times variance of b times r transpose. और वेरिएंस ऑफ बी क्या था आपका? वेरिएंस ऑफ बी आपका सिग्मा स्क्वायर एक्स ट्रांसपोज एक्स इनवर्स आर ट्रांसपोज. सो दिस इज द वेरिएंस ऑफ आर बी. सो नाउ I have got the mean of RB and variance of RB. Let me write it here. So RB is distributed with mean R beta and variance as R sigma square X transpose X inverse. नहीं clear है, I'll repeat this point again, but just let me know if this is clear to you or not.
सर एक बार स्क्रॉल अप करना.
हाँ जी. ठीक है?
ओके सर.
या. ठीक है, shall I move ahead? If there is any doubt, please ask. Do you get the point why I'm talking about sampling distribution of RB? Everyone?
Yes, sir.
Others, do you get why I'm talking about the sampling distribution of RB? Please ask, please don't remain silent, please. अगर दिक्कत है तो I'll repeat from first point and then move ahead. But please ask. Do you understand why I'm talking about RB?
Sir, here X transpose X inverse, we have taken this from the minimization part, yeah?
Which part here?
मिनिमाइज जब हम मिनिमाइज करते हैं
नहीं नहीं, ये तो x ट्रांसपोज x इनवर्स वेरिएंस ऑफ b है ना। OLS एस्टिमेटर का मीन और वेरिएंस यू रिमेंबर।
अच्छा हाँ
b
got it.
b is your OLS estimator, no?
Yes.
Yeah. Guys, please ask अगर थोड़ा सा भी डाउट है, repeat this point again because I'm not going to rush into this topic. So अगर आपको लगता है थोड़ा सा भी डाउट है, repeat this point again, but please ask, please don't remain silent.
So can you explain once again why we are estimating the sample of RB, like what RB follows?
Yeah. You see, अभी हमने क्या देखा कि हमने जितना भी नल हाइपोथेसिस टेस्ट किया या जितना भी हमने एग्जांपल लिया नल हाइपोथेसिस का, all of them fitted into this general linear framework. This is just a it's an implicit function form. You can think like that. So where R was known to me, small r is known to me, and this is beta about which I'm testing the hypothesis. So jitna bhi hypothesis hai, whether beta 1 is equal to 0 or beta 1 plus beta 2 is equal to some value, or beta 1 is equal to beta 2, or beta 1 is equal to 1, any type of hypothesis can be easily fitted into this general linear framework, which is written as r beta is equal to r. Now this beta is not known to us. This is a population parameter. So अगर ये मेरे पास नहीं मुझे पता है तो इसीलिए तो हम OLS estimators को यूज करते हैं. That is, since we do not know about the population parameter, we estimate the population parameter using the method of least square. So I replace this beta by RB. That's the best thing that I can do. और तो मेरे हाथ में कुछ नहीं है. And on the basis of this B, I want to hypothesize or I want to test my hypothesis regarding this beta. Is this clear?
Yes, sir.
तो मैं ये RB कहां से है? अब क्या है? अब क्या है? ये RB क्या है? ये R times B. Wherever OLS estimator is concerned, it means this is the estimated part. And R क्या है? This is the actual part. So so RB minus R times B minus R itself is a statistic. Why I'm saying it's a statistic? Because it is used as an estimator to estimate about R times beta minus R. And since हमारे पास ये बीटा नहीं, इसको मैंने replace किया इस B से. So this RB minus R itself is a test statistic. And then we say that if I have to go for the testing or the testing procedures, I must know about the sampling distribution of this RB minus R. So R तो एक known constant है, again small r एक known constant है. So मेरे पास जो variable बचता है जिसका मुझे sampling distribution की बात करनी, वो this is nothing but this RB part. That is, unless I know about the sampling distribution of this statistic, I cannot draw any inference about the true population. Is this point clear, guys?
Yes, sir.
समझ में आई बात? मैं आर बी की बात क्यों कर रहा हूँ?
Yes, sir.
Sir,
नहीं समझ में आई तो आई रिपीट दिस अगेन, बट प्लीज आस्क. या
सर
हाँ जी.
सर एक स्मॉल क्वेरी है. ये स्मॉल आर जो है सर, इफ वी हैव एक्स एंड वाई डेटा, तो स्मॉल आर जो होगा तो एक्स होगा एंड कैपिटल आर वाई होगा, ऐसा कुछ?
नहीं, इसमें एक्स और वाई की बात ही नहीं आ रही डियर. इसमें एक्स और वाई में इन्वॉल्व ही कहाँ कर रहा हूँ.
तो सर गिवन वैल्यू एंड एस्टिमेटेड वैल्यू थोड़ा सा इसको.
नो, यू सी, व्हेन वी राइट h naught to be beta 1 is equal to 0, अब ये मेरा हाइपोथेसिस है, that is my null hypothesis is that the true population parameter attached to the expected variable 1 is 0. अब इसको मैं टेस्ट करता हूं, मेरे पास बीटा 1, इसको मैं टेस्ट करूंगा यूजिंग B1 ओनली, नो? अगर आपको टेस्ट ऑफ हाइपोथेसिस आपने थोड़ा बहुत किया है, तो हाउ डू यू टेस्ट इट? यू राइट सिंपली, right, and then you say that t test मैं लगाता हूं B1 upon standard error of B1. This is how you test, no?
Yes, sir.
Right? How do you come to this part? Ultimately, you're testing about beta 1 equals 0, not B1 equals 0. You understand this point?
Yes.
है ना? So when I say that this R beta is equal to R, this is what you actually assume to be true. That is, this beta 1 equals 0, this is what you assuming to be true, null hypothesis being true. इसलिए आप test carry out करते हो कि whether I reject my null hypothesis or I am not able to reject my null hypothesis. So जो expected और actual value की बात यहाँ पे यही है कि जो इसको जब मैं बीटा को RB से replace करूंगा तो ये estimated है. This is the estimated value. और यहां पे R क्या है? ये R, this is this 0. सो अगर आप इसको फिट करो, कल हमने देखा था, इसको आप फिट करो, सो R तुम्हारा कैसा दिखेगा? R इज समथिंग लाइक दिस. सो हियर द स्मॉल r इज द 0 नंबर. अब इसको मैं, सिंस बीटा नॉट बीटा 1 नहीं पता है मुझे, तो मैं B नॉट B1 से रिप्लेस करता हूं. सो नाउ दिस बिकम्स माय एस्टिमेटेड पार्ट. And this is the actual which I'm assuming or which I'm thinking to be true. That's what I'm saying, that this is the estimated, this is the actual part. So RB minus R is the discrepancy between actual and estimated portion. Do you understand now?
Yes, sir.
So X और Y की बात नहीं आ रही यहाँ पे अब हम डेटा से अलग आगे जा चुके हैं, because I already have B. I already have estimated my sample, OLS estimators, which is based on the observations. Now, using this B, I am trying to estimate about this R beta is equal to R. That is my linear hypothesis about the population coefficients. Is this clear?
Yes, sir. Yes, sir. Thank you.
Make clear again. I'll repeat this. Anyone? Do you understand why I'm talking about R beta, RB minus R as statistic? अगर किसी को भी डाउट है, please ask right now. नहीं? Sure, shall I move ahead?
Yes, sir.
Okay, all right. So I'll just, write whatever we have discussed till now. So my null hypothesis is R beta minus R equals 0. अब since ये मुझे नहीं पता है, तो इसको मैं estimate करता हूँ using this vector which is written as RB minus R. Right? ठीक है? Now, in order to draw any inference about RB minus R, that is R beta minus R, first step is to compute this vector RB minus R. अब ये वेक्टर क्या है? वेक्टर ये है, ये बताता है डिफरेंस बिटवीन द एक्सपेक्टेड वैल्यू एंड द ट्रू ऑब्जर्वेशन. RB, R pre-multiplied by this OLS estimators is the expected value, and small r is the actual observation that we have. So I assume my null hypothesis to be true. Assuming this to be true, I set up this vector, I compute this vector and find out the difference. If the difference between estimated or expected and actual observation is large, I reject my null hypothesis. Because अगर null hypothesis true होता, null hypothesis क्या है मेरा? R beta is equal to R. That is, there is no difference between, the actual observation and estimated observation. But what I notice is that when I compute this vector using my OLS estimator, the difference between RB and R is quite large. It means whatever difference that exists between cannot just attribute it to random errors. It means it must have come from some other population rather than following this null hypothesis. And that's why you reject your null hypothesis, saying that the difference between the actual observation and estimated observation is statistically significant. And here statistically significant means that the difference or the discrepancy cannot just be attributed to errors of sampling, because ultimately this B depends on the sample. So अगर ये difference quite large है, this difference cannot be attributed to errors of sampling. It means that the difference which exists is statistically significant. That's why you reject your null hypothesis. And if the difference between RB and R is small, what it means is that discrepancy hai, obviously because I'm using the sample estimators. So definitely there is discrepancy between the actual and estimated observation, but that discrepancy is so small that it can be just attributed to errors of sampling. And that's why we do not reject null hypothesis. So the terminology which follows, which we'll see later on, we say that अगर कोई आप null hypothesis reject करते हो तो उसको बोलते हैं statistically significant T ratio. This is what it means. So statistically significant here means that the difference between the actual observation and estimated observation using OLS is so large that that discrepancy cannot just be attributed to errors of sampling. And that's why I reject my null hypothesis that R beta is equal to R. This is not true. Because the discrepancy exists between this in this vector, and that discrepancy is quite large. Compared to the case where discrepancy is there, but that discrepancy is so small that it is almost insignificant in magnitude. And that's why you say that we do not reject the null hypothesis, and then you say that insignificant T ratio. I'll talk about all this once we move ahead. But this is how terminology follows. Is this clear? Is this clear, people? Please respond so that we can move ahead.
Yes, sir.
Okay? Okay, all right. So in order to compute this vector, RB minus R, I must talk about the sampling distribution of RB. So in order to talk about sampling distribution of RB, I must talk about mean of RB and variance of RB. So we know that expected value of beta, that is OLS, ये vector है आपका. अभी हमने simple इसको ऐसे लिखा, but you must always remain open to the idea that this B is a vector and R is a matrix. R, small r itself is a vector. So expected value of beta, B, that is OLS estimator, is your true population parameter. So RB क्या होगा? R is a matrix of known constants, so it will just be R times beta. And similarly, in order to talk about variance of RB, which is we just calculated, so this comes as sigma square X transpose X inverse R transpose. So this is mean of RB, this is variance of RB. So we say that RB का जो sampling distribution है, that is distributed around mean R beta, and variance sigma square X transpose X inverse R transpose. Is this clear?
Yes, sir.
Sure, everyone?
Yes,
Shall
sir.
I move ahead now? Okay, all right. अब देखो, दैट इज OLS एस्टिमेटर. आपने उसको कैसे लिखा? X ट्रांसपोज X इनवर्स मल्टीप्लाइड बाय X ट्रांसपोज Y. कल भी हमने देखा था that if you expand that is you write Y as X beta plus mu, so B becomes a function of mu, that is error term. Now assumption of normality of this error term will automatically mean that this OLS estimator, which is a linear combination of a normally distributed random variable, will also be normally distributed. ठीक है? So I can write this as RB normally distributed with mean R beta and variance given as. यहां तक कोई दिक्कत? Is there any problem till here? Please ask.
No, sir.
ठीक है? ओके, मुझे क्या चाहिए? मुझे स्टैटिस्टिक RB नहीं, मेरा स्टैटिस्टिक है RB माइनस R, राइट? इज दिस क्लियर पीपल? मेरा स्टैटिस्टिक RB माइनस R है.
Yes, sir.
ठीक है. अब
Yes, sir.
या अब देखो RB से हम RB माइनस R पे कैसे जाते हैं. ये मेरा RB है और इसका मीन है R बीटा. अगर मैं इसको एक्सप्रेस करूं इसके डेविएशन अराउंड इट्स मीन से, दैट इज इफ आई डिफाइन माय स्टैटिस्टिक टू बी समथिंग लाइक दिस and take R common, I can write this like this. That is, I have this variable, I express this variable in the deviation form by subtracting each of the raw variable around its mean value. I can write this in this form.
Yes, sir.
ठीक है? So now this will become normally distributed by इसका mean क्या होगा अब इस statistic का?
What mean will be R beta minus beta 0.
0?
Hmm.
So it will be normally distributed with mean 0. Variance will remain unchanged because variance is unaffected by change of scale. Sorry, change of origin.
Change of origin, sir.
Correct? Now, so I have come to this part. RB minus beta is normally distributed with mean 0, variance R sigma square X transpose X inverse multiplied by R transpose. Now, assuming null hypothesis to be true. So, assuming null hypothesis to be true means assuming that R beta is equal to R is true. Am I clear here, dear? So assuming null hypothesis to be true, I can write this as RB minus R is normally distributed with mean 0 and variance given by. Is this clear? So I have
One doubt. Wasn't our null hypothesis RB minus R? Yeah,
come again, dear.
So what was our null hypothesis? RB, like we were testing the difference between RB minus R, right? Yeah,
Correct.
RB.
But null hypothesis तो आपका ये है ना, dear? Null hypothesis is about the population coefficient, no?
So we are testing R beta equal to R, but aren't testing the difference between the estimated value and the actual value RB minus R.
That's what I'm saying कि आपका null hypothesis किसके लिए? Is the null hypothesis for B or beta? Since we do not have knowledge on population coefficient, I replace this by B. But my null hypothesis is on this, not on this.
अच्छा.
Is this clear?
Okay.
मेरा नल हाइपोथेसिस देयर पॉपुलेशन कोएफिशिएंट पे है ना. ये मुझे नहीं पता था, इसलिए मैंने उसको OLS एस्टिमेटर से रिप्लेस किया.
Okay, So aren't we testing whether B is the suitable estimator for beta here?
No, we are not testing whether B is suitable estimator. B already is a suitable estimator for beta, na? Tabhi to we have replaced beta by B.
Okay, sir, understood.
है ना? हमारा testing of hypothesis about the population coefficients पे. Clear?
Okay, sir.
Yeah. So now you have got a sampling distribution for the vector, that is RB minus R, where this vector is a normally distributed random variable with mean 0 and variance given by this term. Okay? Till this point, any problem? I'll repeat this again.
No, sir.
आगे बढ़ूं?
Yeah.
Okay, all right. Now, before we move ahead, there are some important relationships that exist between various, random variables distributed in in different distribution form. That is, mainly I'd like to discuss here the relationship between Z, that is standard normal variate, chi-square, T, and F distributed random variable. I'm sure in the class of statistics you would have been taught about this. Is this the case? Are you aware of the various relationships that exist between such distribution?
No, sir.
No, sir.
Okay, all right. Neil, you are not aware?
So we did not do this in a stats class.
Achha.
So, chi-square ka I do not remember exactly, but I know how to get it from a table.
Okay.
And yeah, and Z and F, I know that you have to square it and you have to find something out of that.
Chi-square is the summation of normal distribution now?
Correct. Yeah. And let us see, you need not memorize this ever again, because this is how all these random variables are, related to each other. So, assume करते हैं कि आपका एक, variable है Z, which is a standard normal variate. I'm sure that you are aware at least what is standard normal variate. Standard normal variate
mean variance one.
Correct. Yeah. Correct. तो आपके पास कोई भी एक x है जो normally distributed random variable with mean variance, let's say sigma square. You transform this normal variable into standard normal variate by subtracting it from mean value and dividing it by standard deviation. And that's how you transform a random variable, normal random variable into a standard normal variate. चलेगा यहाँ तक? ठीक है? So let us say that this Z is a standard normal variable, and standard normal variable means it is distributed, it is normally distributed with mean 0 and variance 1, that is standard deviation, and they are called standard normal variable because they are expressed in standard deviation units. Now, if you take n such values out of this standard normal variate or normal variable, that is, this is a distribution, and if you select n such values out of this distribution and call them, let's say Z1, Z2, select a Zn. Now these are n such standard normal variates which have come from this, let me use this, which has come from this standard normal population. And what I do is, I take these n number of standard normal variables which are drawn independently out of this population and square and sum them. That is, I take each of these n number of variables and I square them first, and then I sum them up. So the statistic that you get, or the distribution that you form when you select n such independently drawn random variable out of this standard normal variate, this statistic is called, or is said to have a chi-square distribution. And chi-square distribution, the beauty of the chi-square distribution is that it's a single parameter distribution family. And by single parameter, I mean that it is only determined by or characterized by one parameter, which is called as degrees of freedom. So when you take n such independent standard normal variates, square them and sum them up, the resultant statistic is called your chi-square distribution. And this chi-square distribution is determined by one parameter, which is called degrees of freedom. And in this case, the degree of freedom here is n. So chi-square distribution is nothing but it is obtained from independently distributed standard normal variate. And how do you obtain them? You take each of those n number of standard normal variate. One second, guys. Hello? Yeah, sorry. So a chi-square distribution or chi-square distribution is determined by one parameter, which is called degree of freedom. So this is the relationship between the standard normal variable and chi-square. Is this clear? Is this clear how you obtain chi-square distribution from a standard normal variate?
Yes, sir.
ठीक है? अब अगर आप chi-square का फॉर्मूला भी देखोगे आपको समझ में आ जाएगा. chi-square का फॉर्मूला हम कैसे लिखते हैं? xi minus x bar divided by sigma इसका square and summation, right? This is the chi-square formula. chi-square statistic का फॉर्मूला आप यही लिखते हो?
Yes, sir.
है ना? And this xi minus x bar upon sigma क्या है आपका? This is z.
So doesn't chi-square also have to do something with the expected value of it?
वो उसका एक यूसेज है नील. That is
Okay.
expected frequency and observed frequency. That is one of the usage where you use chi-square. But ultimately chi-square is a distribution which comes out of the standard normal variate family. ठीक है? Shall I
So
go
Z
ahead?
is the norm, or Z was the Z distribution about you're talking about now, which we have studied in econometrics.
Correct. Z distribution को ही standard normal variate बोलते हैं dear.
Yeah, okay, sir, got
है ना?
it.
आपके पास अगर मान लीजिए x1, xn ये सारे normal random variable हैं. So जो normal distribution का जो PDF होता है, that is quite tedious to write. 1 upon sigma root 2 pi e to the power minus half x minus mu upon sigma whole square होता है. बहुत tedious होता है. So in order to remove this mathematical complexity which are attached with normal distribution, we convert each of those normally distributed random variables into standard normal variate. So standard normal variate is nothing but you transform each of those normal distributed random variable. You
Okay,
take
sure.
each of those distributed random variables, subtract the mean from it, and divide by standard deviation, and that's how you convert each of them to be normally standard normal variate. Chalega?
Yeah, sir. Z was also the population mean minus sample mean, right?
Correct. Yeah.
Oh, okay, sir.
Is this clear to all of you? हाँ जी. Yeah.
So just for clarity, sir, मान ले हमारे पास 10 नंबर है.
हाँ जी.
तो वो 10 नंबर का पहले मैं मीन और एसडी निकाल दो. ठीक है. तो उससे मीन और एसडी से मुझे हर एक वैल्यू का मुझे जेड स्कोर मिल जाएगा.
करेक्ट.
फ्रॉम Z1 to Z10. फिर मैं उन सबको स्कोर करूं, स्क्वायर करूं.
करेक्ट.
और सम कर दूं. तो दिस इज माय chi-square value for this distribution.
करेक्ट, वो आपको वो जो देखो ये Z है, T है, ये सारे स्टैटिस्टिक होते हैं. These are the formulas, right? So when you square each of those, 10 numbers that you have got out of the standard normal variate, the resultant distribution that it will follow will follow chi-square distribution. तो उसका shape अब कुछ chi-square type follow करेगा. Did you understand this? ये हुआ इसका मतलब.
Yes, sir.
है ना? So it will be a chi-square distributed random variable with degree of freedom, in this case 10, जो भी आपने example लिए. चलेगा?
ठीक है सर.
ठीक है? One important thing is that mean of a chi-square distributed random variable with degree of freedom n, that is mean of a chi-square distributed random variable with degree of freedom n is your n, and variance is twice of n. This is nothing but the important result that we have as far as chi-square distributed random variable is concerned. ठीक है? Is this clear, all of you? chi-square को हम z से कैसे obtain करते हैं? Is this clear?
Yes, sir.
So you should understand that chi-square is nothing but sum of squared values of independent standard normal variables. ठीक है?
एक्सपेक्टेड वैल्यू और वेरिएंस का क्या लिखा है आपने साइड में?
Come again, dear.
Expected value of chi-square and variance of something you have written. What is that?
ये variance of a chi-square distributed random variable है, dear. कि mean of a chi-square distributed random variable is equal to degree of freedom. That is, one parameter, and variance of the chi-square distributed random variable is twice of that degree of freedom.
Okay, sir. ठीक है.
चलेगा? Shall I move ahead?
Yes, sir.
Okay, all right.
सर
हाँ जी.
सर इसका implication
एकदम आवाज नहीं आ रहा है. Please speak louder.
सर इसका implication वगैरह मुझे बहुत क्लियर नहीं है, तो सर उसका थोड़ा सा पार्ट बता दीजिए सर.
Implication क्या, dear? chi-square.
या
chi-square आपने पढ़ा है?
यस सर, पढ़ा है, कुछ एग्जांपल्स भी किए हैं, बट वो ऐसा क्लैरिटी नहीं है कि एग्जैक्टली.
So I'm just drawing the relationship between chi-square and z, dear. All I'm saying that कि chi-square ये सारे डिस्ट्रीब्यूशन है, जैसे नॉर्मल डिस्ट्रीब्यूशन हुआ, टी डिस्ट्रीब्यूशन हुआ, इसी तरह chi-square एक डिस्ट्रीब्यूशन है. इट्स अ फैमिली ऑफ डिस्ट्रीब्यूशन. इसका ये प्रॉपर्टी ये है कि एक तो पहला नंबर chi-square is the moment it's squared, so it will always be a skewed distribution, unlike the normal and t distribution that we are so much engrossed in understanding. क्या यहाँ पे वो है कि chi-square को हम कैसे पढ़ सकते हैं या chi-square को हम कैसे खुद फॉर्म कर सकते हैं. तो उसमें हमने क्या देखा कि chi-square is sum of independently distributed squared values of normal variate. Z values तो पता है आपको?
यस सर.
है ना? Z values से हम chi-square पे कैसे जाएंगे? That's what I have discussed. I have discussed nothing. अब इसका एप्लीकेशन के लिए मुझे स्टैटिस्टिक्स पे जाना पड़ेगा, dear. Which is where you use आप कहाँ पे chi-square distributed random variable use करते हो? जो भी example था, when we compare goodness of fit, or when we compare observed frequency with the expected frequency. जब मुझे इंडिपेंडेंस निकालना होता है टू रैंडम वेरिएबल्स के बीच में, वहां पे आप chi-square का यूज करते हो. एक साइड पे आपका x है, एक साइड पे y है. अब मुझे डिफाइन करना है और मुझे डिटरमाइन करना है whether x and y are independent or not. That's where you use these concepts, chi-square. Observed frequency देखो और expected frequency on the basis of this formula, summation xi minus x bar upon standard the whole square. And then you compare whether the observed frequency and expected frequency are same or not. That is done on the basis of chi-square. Again, जितने भी आपके sum of squares हैं, like explained sum of squares, residual sum of squares, total sum of squares, जो कि econometrics में use होते हैं, वो सारे chi-square distributed random variable होते हैं. That is, the distribution that these sum of squares follow are chi-square distribution. तो इसका प्रैक्टिकल एप्लीकेशन है आपका अनोवा टेस्टिंग. जब आप करते हो एनालिसिस ऑफ वेरिएंस में, अनोवा टेस्टिंग में क्या है? अनोवा टेस्टिंग में वी यूज एफ टेस्ट, एंड एफ टेस्ट इज नथिंग बट रेशियो ऑफ टू इंडिपेंडेंटली डिस्ट्रीब्यूटेड chi स्क्वायर वेरिएबल्स. सो जब आप आर स्क्वायर को देखो, आर स्क्वायर इज ESS अपॉन TSS. ESS is sum of squares, TSS is sum of squares. So ultimately ESS is a chi square distributed random variable with degree of freedom given by n minus k, and TSS is also chi square distributed random variable with degree of freedom given by n minus 1. So these are some of the practical applications of chi square distribution. Is this clear?
Yes, sir.
Sir,
हाँ जी, yeah.
एक डाउट है रिगार्डिंग एफ टेस्ट. शुड आई आस्क लेटर व्हेन यू आर टीचिंग इट, और अभी पूछ
हाँ,
लो?
अभी मैं एफ पे आ ही रहा हूँ नील.
ठीक है.
उसमें उसको एड्रेस करते हैं, ठीक है?
हाँ जी सर.
Yeah. Okay, so having determined the relationship that exists between Z and chi square, let us go and understand another important distribution which is called student's T distribution. So T distribution को हम कैसे define करते हैं? T distribution is defined in terms of a standard normal variate and an independent chi square distributed variable. Again, I'll say T distribution is defined as a ratio of a standard normal variate and an independent chi square variable. So let us see how do we actually write T distribution. So suppose, again I have a standard normal variate written as Z. So standard normal variate है तो वो ऐसे, it is normally distributed around mean 0 and 1. And let us say that I have a chi square distributed random variable. So let's say Y is chi square distributed random variable with degree of freedom given by n. अभी हमने क्या बोला? That T distribution is a ratio of two independent variables where one variable is a standard normal variable and the other variable is a independent chi square distributed variable. So I can define my T as Z upon, अब ये chi square है, ये ऊपर standard normal variate है, तो I convert this chi, that is I take the under root of this chi square. So I can simply write this as under root of y divided by, that is I take the chi square distributed random variable and I divide it by its degree of freedom. So this is my T distribution. अब अगर तुम्हें थोड़ा सा भी एकदम थोड़ा क्लिक करता है तो यू गो बैक योर टी टेस्ट. टी टेस्ट में हम क्या करते हैं? We take the coefficient, let's say bi, and we divide it by its variance of bi. Variance of bi is nothing but, standard deviation of bi. And standard deviation of bi is nothing but under root of variance. A variance is a square, so variance is a chi square distributed random variable. Variance क्या है? Variance is a variation divided by degree of freedom, if you remember from our earlier lectures. So जो T test है आपका और T distribution है, it's a distribution which is made up or which is made by or which is made as a ratio of two independent variables where the numerator is a standard normal variable and the denominator is an independent chi square variable with the appropriate degree of freedom. Is this clear?
Sir, very sorry. आप प्लीज स्मॉल y क्या है बोल पाएंगे?
This y is a variable which follows a chi square distribution. This z is a variable which follows a standard normal variable. So T is defined as ratio of a standard normal variable and a chi-square distributed random variable.
तो सर ये z हमें निकालना आता है, हम ये y कैसे निकालेंगे अगर हमारे पास कुछ डेटा हो तो?
y तो इजीली z से ही निकलेगा ना नील। जैसे देखो मीन है आपके पास, मीन फॉलोज अ स्टैंडर्ड नॉर्मल वेरिएबल, मीन से आप वेरिएंस कैसे निकालते हो?
अच्छा सर, आप बोल रहे हो क्या y इसी डेटा का chi स्क्वायर है?
करेक्ट। और
ओके,
दोनों इंडिपेंडेंटली डिस्ट्रीब्यूट, ऑब्वियसली बिकॉज ये chi स्क्वायर तो इंडिपेंडेंट डिस्ट्रीब्यूशन है इससे, तभी आई हैव डिवाइडेड बाय इट्स डिग्री ऑफ फ्रीडम, नो n। ठीक है?
यस सर, यस सर।
T distribution is a ratio of a standard normal variable and a chi-square distributed random variable. चलेगा? चलेगा all of you?
Yes sir.
Okay. And guys, these are statistics related things. I thought you guys would be knowing, but anyway. Next, let us look about F distribution. अब जैसे T distribution एक ratio distribution है. Ratio means कि it's a distribution which is made by dividing a standard normal variable by its chi-square distributed random variable. उसी तरह F distribution is a ratio of two independent chi-square distributed random variable. So what I'm saying here is that suppose I have a chi-square distributed random variable y1 which follows a chi-square distribution, let's say with degree of freedom n1. I have another chi-square distributed random variable, let's say given by y2, which follows chi-square with degree of freedom n2. One second, guys. So how I'm defining my F? I'm defining my F as ratio of two independent chi-square distributed random variable. So I define my F as y1 by its own degree of freedom, y2 by its own degree of freedom. So your F distribution is nothing but ratio of two independent chi-square distributed random variables with degree of freedom or with their respective degrees of freedom. Is this clear? अब इसका एक प्रैक्टिकल एग्जांपल देखो, जो हम F टेस्ट करते हैं एनोवा टेस्ट में, वो हम F टेस्ट लिखते हैं ESS upon some degree of freedom upon RSS upon some degree of freedom. Now ESS is a chi-square distributed random variable because it's a sum of squares. It has a degree of freedom. So F test मान लेते ये y1 मान लेते ESS है मेरा, y2 मान लेते RSS है मेरा. y1 that is ESS is a chi-square distributed random variable with a degree of freedom, let's say given by n1. RSS is another chi-square distributed random variable with a degree of freedom given by n2. So F ratio is defined in terms of these two independent chi-square variables. चलेगा?
So, what do we mean when we use this word independent?
Independent means कि वो एक दूसरे के probability को impact नहीं करते हैं. तो ESS और RSS independent है, अगर आपको याद होगा, by this orthogonality of vectors. That's why we are able to write TSS as ESS plus RSS. Remember? This is my estimated Y, this is my residual vector, and since uske beech mein 90 degree ka angle hai, that's why you are able to write Y as sum of this plus this component. So ESS and RSS, they are two independently distributed chi-square variables.
Okay, sir. Got it.
Statistics में आप independence कैसे बोलते हो? When you say two variables are statistically independent, what do you mean by that? What do we mean by statistical independence? Anyone?
Maybe no autocorrelation.
Come again?
Sir, no autocorrelation. Yeah.
No autocorrelation? Ayushi, what do you mean by statistical independence? Manna, what do you mean by statistical independence?
So the variables do not influence each other.
And how do we exactly write it statistically?
Sir, I think the expected value of A and B happening at the same time depends on equals to expected value of A times expected value of B.
Correct. Correct. Guys, ये सारी चीजें absolutely clear होनी चाहिए, otherwise you'll face lots of problems later on. We say that two variables x and y are statistically independent if their joint probability is equal to sum or is equal to product of two marginal probabilities. So probability of x conditioned on y should be equal to probability of x multiplied by probability of y, their respective marginal probabilities. That's how you define statistical independence. And that's how you say कि अगर कोई दो वेरिएबल इंडिपेंडेंट है तो एक के अकर होने का प्रोबेबिलिटी दूसरे के अकरेंस को डिस्टर्ब नहीं करता है. Because otherwise things will be really you just learn all these things but conceptually तो clear नहीं होगा कुछ भी. So please revise all these things because ultimately I am telling this for you only because these are some of the interview questions which are asked a lot. इंडिपेंडेंस क्या है, म्यूचुअल एक्सक्लूसिव इवेंट्स क्या होते हैं, कोरिलेशन रिग्रेशन क्या डिफरेंस है, कोरिलेशन और इंडिपेंडेंस का क्या रिलेशन है. And these are very, very pertinent interview questions, whether you appear right after masters or even when you change or shift jobs between the jobs. अगर आप statistically related या इस टाइप में काम कर रहे हो तो. Sorry. Anyway, so summarizing what we have learned till now or what we have discussed till now as far as relationships between variables are concerned, first thing that we understood was that a chi-square distributed random variable with n degree of freedom is nothing but sum of squared values of n independently distributed standard normal variables. So let me write it here. ये पहला रिलेशन हमने देखा. सेकेंड हमने क्या देखा, दैट जो टी डिस्ट्रीब्यूशन है, टी डिस्ट्रीब्यूशन इज डिफाइंड एज अ रेशियो ऑफ टू independently distributed random variable where in the numerator you have a standard normal variable and in the denominator you have an independent chi-square variable. So t can be thought to be written as z upon y by n. Third, what we looked at was, that f distribution is ratio of two independently distributed chi-square variable. So f can be thought of as a ratio of two independently distributed chi-square variable, and we just understood that chi-square distribution is a family of distribution distinguished by one parameter, and that parameter is called your degree of freedom. So F is a ratio of two independently distributed chi-square random variables. और यहीं से एक बहुत ही रिलेशन आता है F और T के बीच में. वो क्या है? You look at the expression for T here. If you square this, that is, if I do square of T, so I write it as Z square upon Y upon N. And I can think of writing this as Z square upon 1 Y upon N. So this is T square. Now you understand that now this is Z square, so it's a chi-square distributed random variable. Y was already defined to be a chi-square distributed random variable with degree of freedom N. So it is said that a squared T distribution, or if you square the T statistic, you get a F distribution of 1 degree of freedom in numerator and n degree of freedom in denominator. So if there is a T distribution which has n degree of freedom, so square of a T distribution having n degree of freedom is equal to F distribution having 1 degree of freedom in numerator and n degree of freedom in denominator. This is a very, very important relationship between T and F. Is this clear?
Could you please repeat this, sir?
Yeah. ये मेरा T expression है, इसमें तो कोई दिक्कत नहीं है आपको. T is a ratio of
Sir, we have lost your voice, or I don't know if it's only me.
No, sir is not audible.
freedom. Am I clear now? Are you able to hear me?
We were not able to hear you, sir.
Are you able to hear me now?
Yes, sir.
Okay. What I'm saying here is that square of a T distribution with n degrees of freedom is equivalent to an F distribution with 1 degree of freedom in numerator and n degree of freedom in denominator. Is this clear? Is this clear, everyone?
Sir, just sir, again, this is just a silly doubt, sir. We know that T is a Z distribution over a chi-square distribution.
Correct.
Right. But when we find the T statistic of a certain number, we are basically finding the Z value of a certain observation divided by the chi-square of the entire distribution.
Correct.
Right. So when we are squaring T square, the numerator technically is not an F, because sir, the numerator is only a single value of Z. It is so sir, sigma T square rather will be a F test.
No, you're not getting. T का numerator क्या है? Z है.
Sir, एक Z, it's a single Z stat.
Correct.
Right.
See, so T का numerator is a Z variable. ठीक है? When you square a Z variable, it follows a chi-square distribution. That's why I'm saying it has a degree of freedom 1 because there's only one standard normal variable.
Oh, okay, yes, sir. Okay, so एक ही value है, sir. हाँ.
Correct. That's why it has a degree of freedom 1, dear. इसीलिए जब आप n number of such standard normal variable को आप square और sum करोगे तो वो chi-square with n degree of freedom होता है. Is this clear?
Yes, sir. Understanding, sir.
ठीक है? Is this clear to all of you?
Sir, understood the theory, but sir, just एक और doubt. This is what is the practical application of a t-square? Is there one, or it is just to show relationship?
अभी जब हम hypothesis testing करेंगे ना नील, involving all this, so what we'll find is that when you have a simple linear hypothesis about population parameters, then you are free to use either t-test or f-test because they are interchangeably used. ठीक है?
Okay, sir.
जैसे normally you write your t-test as b upon standard error of b, right? It follows a certain degree of freedom. For the timing, let me say that this has a degree of freedom n. तो ये क्या हुआ इसका मतलब कि if I have a simple linear hypothesis about the population coefficients, I can either go for t-test or I can either go for f-test as well. F-test कैसे निकालूंगा? I'll simply square this t statistic. So my f-test will be b square upon variance of b.
Sir?
हाँ जी.
So isn't T and Z also used interchangeably?
Isn't T and Z also used interchangeably? No, dear. Z is only used when you are aware of the population variance. You cannot use, or you should not use rather, when you have only sample variance. And that's why even in the Z test, mostly you use T statistic. So these are statistic. Please forget using the word test for now. Whether it is Z or T or F, they all are a statistic. When you use such statistic to test a hypothesis, that's why it is called Z test or T test. Otherwise, they are not test. Is this clear?
Yes, sir.
और यही difference है using Z or T में, when you say, when I don't know, someone had asked in very earlier of my lectures कि एक hard and fast rule है कि अगर sample size greater than 30 है तो use Z, or less than 30 use T. This is the main difference between Z and T statistic. That is, a T statistic is a ratio of a Z statistic or a standard normal variable and a chi-square distributed random variable. And that's why T distribution involves a parameter which is called degree of freedom, which Z distribution does not have. Do we understand this difference?
Yes, sir.
ये clear है आप लोग को? Please do not use the word test unless you are conducting the test of hypothesis using these statistics. Understand them as statistic. ये बातें clear है आप लोग को?
Yes, sir.
नहीं clear है? I'll repeat this again, but please ask. Is the relationship between various variables distributed in different distribution clear to all of you?
So,
हाँ जी.
ये जो B है, it is a random normal distribution, right?
कौन सा डियर? एक सेकेंड. T, ये T?
B. T is given by B upon standard error.
ये B.
Yeah.
ये B तो आपका, ये तो मैंने एग्जांपल लिया ना भूषण, ये B है आपका those OLS estimators.
All right.
जब हम एक मिनट बस, ये आपका पॉपुलेशन रिग्रेशन फंक्शन है, आप इसको एस्टिमेट करते हो एक सैंपल रिग्रेशन फंक्शन से, राइट? ठीक है. अब मान लो मेरा नल हाइपोथेसिस है. आप नल हाइपोथेसिस तो ऐसे ही लिखते हो. You do not write your null hypothesis to be B1 is equal to 0. Always remember this. You write your null hypothesis as that the population coefficient attached to the explanatory variable 1 is 0. And then you test for this null hypothesis. So you write your alternate hypothesis as beta 1 not equal 0, right? ठीक है? तो अब टी टेस्ट कैसे लिखते हो डियर? टी टेस्ट आप लिखते हो B1 माइनस एक्सपेक्टेड वैल्यू ऑफ B1 divided by standard error of B1. This is the true statistic. Am I clear?
Okay, sir.
Now, what did I tell you कि जितने भी टेस्ट हम अभी प्रोसीड करते हैं उन सब में भी assume our null hypothesis to be true. ठीक है? So I know that expected value of B1 is beta 1 and assuming null hypothesis to be true, so beta 1 equals 0 and that's why you simply write T statistic as B1 upon standard error of B1. You simply forget this part because you think it is for granted. Am I clear?
Yes, sir.
ये बातें प्लीज याद रखिएगा कि assuming null hypothesis to be true, that's why you are able to write simply statistic as B1, that is coefficient value upon standard error. अगर ये यहाँ पे hypothesis में beta 1 is equal to 1 रहता है, यहाँ पे ये -1 word term आएगा. Am I clear? Obviously, I'll talk about all this when I discuss the hypothesis testing, but these are some of the very important things, very small things which must be clear to you, all of you. Is this clear?
Yes, sir.
Okay. So, guys, I'll stop here because I'm not feeling that well. Like I have running nose, but I request for an extra lecture this week. कब आप लोग फ्री हो दोनों क्लास मिला के एमएससी इको एंड फाइनेंशियल इको? कैन यू गिव मी अ टाइम प्लीज?
So for financial economics post 1:30 only, we have classes every day till 1:30.
Okay. And what about MSc Eco?
So tomorrow we have no classes.
तो क्या कल हम मिल सकते हैं क्या? मॉर्निंग में फाइनेंशियल इको do you have any class?
Yes, sir, we have a class at 9:30.
किनका क्लास है वो?
So I'll just check. So we have corporate finance. So sir, Rahul sir.
Rahul Gole, right?
Yes, sir.
ठीक है, I'll talk to him. अगर if he agrees, then I'll take his lecture. Otherwise, 1:30 onward, can we meet? Let's say 2:30 to 4:30 tomorrow.
MSc Eco has a class from 2:30 to 4:30 on Wednesday.
किनका?
Savita ma'am, growth class.
I'll talk to her. Savita ma'am का class I can take because she had already taken one of my lecture. So I'll talk to Savita ma'am. Financial eco people, you are free from 2:30.
Oh yes, sir, we are free from 2:30.
So let us meet tomorrow at 2:30. So we'll have an extra lecture on tomorrow. चलेगा?
Okay, sir.
Sir.
Relationships, please understand them, please revise them, whatever we have done, so that I'm able to finish at least my. And I just want to cover hypothesis testing in tomorrow's lecture. So जितना जल्दी खत्म हो जाएगा उतना जल्दी I'll leave you guys, so that from next week, that is Monday and Tuesday, I'll just deal with computer exercises. So please revise what we have done today, and I'm really sorry. I'll just go do some Okay, so thank you so much for being in the class, and just stay safe, guys, and please revise whatever we have done today. Please, it's an earnest request.
Sir?
Yeah.
ये जो स्टैटिस्टिक्स और नॉर्मल डिस्ट्रीब्यूशंस आपने आज समझाए उसके कोई नोट्स है आपके पास? या फिर
उसमें नहीं होगा, I guess होना चाहिए. नील ने जो नोट्स भेजा हुआ उसमें, या तो you can find this easily available in any of the statistical textbook. सब जगह होगा.
Sir.
हाँ जी.
Sir, in your notes, जो projection वाला part है, could you take that up also tomorrow?
ठीक है.
Okay, thank you, sir.
Yeah. That projection matrix and projection vector you're talking about?
Yes, sir.
Okay. ठीक है. Okay then. See you tomorrow at 2:30. Till then, stay safe. and take care of all others around you.
Thank you, sir.
Yeah.
Thank you, sir.
Thank you, sir.
Yeah.
Thank you.
Thank you, sir.
Thank you, sir.
Thank you, sir.
Thank you, sir.